Recording. All right, good. Okay, so welcome everyone to the February IGRI research seminar. Um, my name is Devormandam. I am the coordinator for the IGRI. And before I introduce our presenter and yield the floor over to her, just want to do some quick announcement at the top, which is that I wanted to draw everyone's attention to the three major IGRI events that are happening this year and that we have registration / applications going on for. We've got the institutional analysis training, which takes place from April to May. We've got our doctoral student workshop, which also happens in May. And then we have our third annual virtual conference that is happening in June. So we've got some of the deadlines for those things are coming up. So for the doctoral workshop and for the conference, the deadline to submit application materials for that is March 1st. So if you're thinking about doing either or both of those, just put it on the radar that deadline is coming up. The deadline for the institutional analysis training is April 1st. I will drop in a link to the homepage for the IGRI in the chat. And so if you go there, you'll see right on the homepage, there's the upcoming events, and you'll see the links to all of those events. So if you want to find out more about what those are about, what are the requirements to apply, and so on. So just wanted to put that out there for everyone. And of course, feel free to circulate and pass along to other people who you think would be interested in any or all of those events. All right, now we'll hand the floor over to our February presenter. I'm just going to introduce her. So Nieves Montes is a PhD student at the Artificial Intelligence Research Institute, which is part of the Spanish National Research Council. Her research interests include multi-agent systems, automated reasoning, and agent-based and social simulation. Her work has appeared in several publications, including the Journal of Artificial Intelligence Research and Artificial Intelligence. Her presentation today is titled A Computational Model of Ostrom's Institutional Analysis and Development Framework. Nieves, I yield the floor to you.
Okay, thank you very much for your introduction. I'm going to share my screen now. And okay, can I get a thumbs up if okay, great, thank you. Okay, hello everyone. I'm Nieves Montes. As David said, I'm a PhD student at the Artificial Intelligence Research Institute in Barcelona, Spain. And today I will be presenting to you the work we have published in a paper titled The Computational Model of Ostrom's Institutional Analysis and Development Framework. I'm going to, obviously because of time constraints, I'm going to do sort of a high-level introduction. There are many low-level technical details that you can find in the paper if you're curious about it, or you can ask about me later in the questions or over email. So just to give you a bit of context on myself, this is a joint work that I'll be presenting with my supervisors, Nieves Ostrom and Carla Sierra. I believe Carlos is also joining us today. We are working at the Artificial Intelligence Research Institute, which was established in the mid-90s. We are based at the Autonomous University of Barcelona campus, but which is 20 kilometers or so from the city, but we are affiliated with the National Research Council. Currently, there are about 20 scientific researchers and also around 20 PhD students, but we expect to grow that number within the following months and years. The institute is, I would say, loosely divided into three departments: logic and reasoning, learning systems, and multi-agent systems, which is the one that we are affiliated with, and where we do work on normative multi-agent systems, electronic institutions, social simulation, trust and reputation models, and automated negotiation. Just to cite some topics. So first, I'm going to provide some background on the Institutional Analysis and Development Framework. I'm sure that many of you in the audience know more about this than myself. But an overview is that the IED framework outlines the universal variables that make up any social interaction and delineates them quite clearly. And so according to it, there are 3 sets of exogenous variables: the physical conditions, the attributes of the community, and the rules. And jointly, these determine how a social interaction plays out. So how this action situation is structured, into which participants take decisions, they bring about joint outcomes. And of course, these outcomes can then refit into the rules in place, which is the set of exogenous variables that is most suitable to change in the in the short to medium term. So in this paper that we have published, what we are providing is a computational framework to automate the institutional analysis process using the IED framework. To do this, we are providing 2 main components. The first is a logic-based language, which we call the action situation language, with which we can systematically describe action situations. And then we are also providing a game engine that takes as input these descriptions using this language and automatically interprets them and builds an extensive form game model out of it, which can then later be analyzed using standard game theoretical tools. Some important features of our model is that the precise decision-making model for the agents that will be participating in the interaction is not set. So we are agnostic with respect to that. The user can use whichever one they'd like. Another is that the language that we're providing has very much in mind the machine readability and interpretability aspects. So it has this very well-defined syntax, which I'll present later. And finally, because it is grounded into a game model, it can be easily integrated with the standard game theoretical tools. So this is the outline of our contribution. First, we have an action situation description, which is written in the syntax that I will present later. This is fed to the game engine that automatically interprets it and builds the extensive form game model of this description, which is then analyzed using whichever solution concept from game theory you would like. So I will first give some necessary background on game theory, just very briefly. So game theory is a discipline that builds and analyzes formal models of multi-agent interactions. The benchmark in this field is the prisoner's dilemma, which I'm sure many of you have heard about, where we have 2 prisoners that have been caught for some crime. They can either confess to the police or remain silent. If they both confess, they get 5 years in prison. If one of them confesses while the other remains silent, the confessor gets to go free, and the other one gets the maximum sentence of 20 years. Or if they both remain silent, they get a lower sentence because it's supposed that the police don't have enough evidence on them. And so within this this model, one of the most popular ways to predict which strategies players are going to be follow is to analyze the incentives with what is called the Nash equilibrium. So in this case, if you are prisoner A and you are assuming that the other prisoner B is going to confess, it's better for you to also confess because you're going to get 5 years instead of 20. Meanwhile, if you are assuming that the other prisoner is going to remain silent, then you should also confess because you will get to go free instead of getting a 1-year sentence. In the game theoretical jargon, we say that the strategy to confess dominates the strategy to remain silent. So the same type of reasoning that applies to prisoner A also applies to prisoner B. And the equilibrium outcome is that both players should confess and they should both get a 5-year sentence, even though they would both be better off getting a 1-year sentence. Again, in the game theory field, we call that the equilibrium outcome is not Pareto optimal. So this kind of table representation of interaction is called a normal form representation, but in game theory, we have a richer way of representing interactions, and that is using extensive form games, where games are representing using these three graphs, where the edges correspond to actions and the nodes correspond to the intermediate or eventually the final states that are reached. And well, they have some advantages over normal form games in that they can represent several actions per player, and they also explicitly encode any stochastic effects in the environment. Okay, so that is for game theory. I will also now give a very, very brief overview on logic programming, which is a bit striking if you haven't encountered it before. So in a logic program, we have facts and rules or clauses. Facts are composed by a predicate symbol that takes in some arguments that are grounded to constants. And we distinguish constants because their first letter is lowercase. And so these express facts about the problem. Let's say, so here we are expressing that Art is the parent of Bob, Art is also the parent of Bea, Bob is the parent of Carl, and Bea is the parent of Co. The other component of a logic program are the clauses, which have a head and a body. In the example, the head is stating that A is the grandparent of C, where both A and C are variables, and you can recognize variables because they start with an uppercase letter. And the way that you read this is that if A is the parent of B and B is the parent of C, then A is the grandparent, of C. So if the conditions in the body hold, then the fact expressed in the head of the clause is true. So when we have a logic program, we can run queries on it. So we can ask it about the facts that we would like to know about. So for example, we can ask a program to find the pairs of grandparent and grandchildren according to the data that it has. So for example, given the facts in this example, the return values would be that Art is the grandparent of Carl and Art is the grandparent of Co. Or in another example, we can ask it about who are the children of Art using this query. And in this case, it would find that the children of Art are both Bob and Bea. Okay, so those is for some preliminaries to help you understand the work in the paper. So now I will go through each of the components of our model step by step. So first I will go through the syntax of the action situation language that we provide. So the way that we are writing action situation descriptions is split into three files. So states.pl, agents.pl, rules.pl. This .pl extension refers to Prolog, which is the language on top of which ACL is implemented and which is a logic programming language. And these three files roughly correspond to the three sets of exogenous variables that are identified in the IED framework. Oops. So first we have the agents.pl file, which encodes the information related to the variable attributes of the community. So here we have a excuse me. Okay. Yeah, in the agents.pl file, we have the compulsory declaration of agents using this agent reserved predicate. So for this exposition now, I will be following the example of the iterated prisoner's dilemma. So in this case, we have two agents, both Alice and Bob. And in case we wanted to declare some additional attributes about the agents, this would also be the place to do it. So we can, for example, declare information about their age or about their profession. And the recommended way to do it is to use a predicate symbol for the name of the variable that we want to declare with two arguments. First is the agent, and the second is the value for that variable. Okay. Next, we have the states.pl rules, which roughly contains the information related to the biophysical conditions of the agent. There's iterated prisoner's dilemma because it is complete, let's say, totally artificial example, doesn't really have that many quote unquote biophysical features, but anyway, just bear with me. So in this file, what we are doing is first we're going to declare the predicates that characterize states. So for this example, we have payoff facts, one for each agent, a counter for the number of rounds, and then we will also be having counters for the consecutive number of defections for each player. Here we are also declaring the initial conditions at the start of the interaction. So for example, we are first declaring that prisoners start with a payoff of 0, that the number of rounds is also initialized to 0, and that the consecutive defections per player are also initialized to 0. And finally, the terminal conditions, and in this case, we're setting the interaction to stop after 3 rounds of the prisoner's dilemma. Finally, one other important piece of information that is carried in the states.pl file are the incompatibilities between facts, and this is declared using this incompatible predicate. So the first argument to this predicate is a fact, and the second predicate is a list. And you should read this as the fact in the first argument is incompatible with the facts in the second argument. So in the example we have here, we're stating that for every state of the game, there can only be one rounds fact, and that for every state of the game, there can only be one payoff fact per player. Okay, so finally, the probably most interesting part of an action situation description is the rules.pl file, where we are declaring the information of the rules variable, that is, so the statements that are regulating how the interaction proceeds. This is the general syntax that we have for our rules, which have 4 arguments. The first is an identifier that denotes the action situation where the rule in question applies. The second is a type, which can have one of 4 values, so either boundary, position, choice, and control. And the role of this type is to indicate to the game engine when that rule in question should be queried. You'll see that these types are reminiscent of the classification of rules according to the aim field in the institutional grammar, according to the aspect of the interaction that they are regulating. In our case, this is it is also inspired by that classification, but the mapping is not one-to-one. So for example, boundary, position, and choice rules are quite straightforward. They're regulating participants' position and actions. But for example, the control rule at this stage of our model is responsible for sort of the control variable and also the costs, and also indirectly the output. And meanwhile, for the information variable, we are really really don't have a dedicated rule type for that, which makes things quite more complicated in game theory. Okay, the third argument of rules is this priority, which is a non-negative integer starting at 0. So the set of rules that have priority 0, we refer to those as the default rules. And then if additional rules want to be added on top of those should be added using higher priority, so over 0. And the function of this priority is to indicate to the game engine how conflicts should be solved between rules that have contradicting consequences. I will not go into details about the mechanism by which conflicts are solved, but if you'd like, the paper goes into great detail about that. And then finally, the last argument of rule statement is the content, which is expressed as an if then where statement. So given some conditions, then some consequences follow, subject to some constraints. And this content is further syntactically restricted by the type of the rules, and I will show this to you now when we go through the example. Yeah. Okay. So for the prisoner's dilemma game, here I'm showing the quote-unquote simple rules, which are boundary, position, and choice rules. So first we have the boundary rules, which are regulating who can enter the action situation. So the content for these rules is as an if agent then participates. So in this case, we're declaring that any agent can participate without any restrictions. The position rules are regulating the assignment of participants to roles, and it follows the syntaxes of if participates variable, then the role that is assigned to this variable is whichever, where some constraints may apply. So, and in this case, again, we are assigning all participants to the role of prisoner, no further constraints. And then finally, the choice rules assign roles to actions. And again, they follow the simple syntax that if someone has been declared to have a role, then it can take some action where some constraints may apply. Again, in this case, we are assigning anyone who has the role of prisoners to the action of either cooperate or defect. So this would be analogous to the confess and or remain silent actions of the example without any further restrictions. So now we move on to the control rules, which are somewhat more sophisticated because they are controlling actually how the system, how the state of the system of the interaction evolves. So I will go into details of the syntaxes of the first rules, and then the other three are analogous. So here we are stating that if does player one some action, this under bar is called the blind variable. So this refers to any value. So if does P1 some action and does P2 some action, so here we have a concatenation of actions to reflect the execution of joint actions, then, and the consequences now is a list where every possible consequences is typed some probability with this operator with prob. This is made so that we can express stochastic effects, but in this case, we just have that the counter for the rounds is set to m with probability 1, where P1 and P2 is different. This is the meaning of this first element in the constraints. The current counter for the rounds is n, and m is n plus 1. So we're just increasing the rounds counter by 1. And the rest of the rules read similarly to this. So for example, in the second, we are regulating what happens if player 1 cooperates and player 2 also cooperates, then their payoff goes to y1 and y2 respectively, again with probability 1. And these y1 and y2 are related to their current payoffs, x1 and x2, in that they are increased by 6 units. So this is how you use control rules to express the evolution of the system. Okay, so I have now presented how we can describe action situations using this language. Now I will describe a little bit how they are automatically interpreted. This is the function of the game engine that has these two components. The first is an interpreter.pl file, which is a prolog script, which queries the rules to see which ones are active, and then processes their consequences and also resolves conflicts between rules. And then we have the build.py script, which is a Python script, which assembles the extensive form game given the results that are fed into it by the interpreter. So I will just go very briefly over how this interpretation and game building process goes. So first we're going to get the participants, then assign roles to them, then get the initial conditions for the interaction, and then enter this loop where while the terminal conditions are not met, we are getting the possible actions from choice rules and finding what are their consequences from the control rules. So first, we need to get who is participating into the interaction from the boundary rules. So in our example, we have two declared agents and a boundary rules that states that any agent gets to be a participant. So the consequences of this is straightforward. Both Alice and Bob, which are the agents declared, become participants in the action situation. Then we need to assign roles to these participants. And again, this is quite straightforward in this example. So we now have two participants. We have a position rule that assigns all participants to the role of prisoner. So naturally, the consequence is that both Alice and Bob adopt the role of prisoner in this action situation. And then the last of these sort of pre-processing steps is to get the initial conditions. So in our states.pl file, we have stated that the initial conditions is that the payoff equals 0 for anyone who adopts the role of prisoner, and also that the round counter is initialized to 0. So naturally, we get these three facts for our initial conditions on the payoffs for both Alice and Bob and the rounds counter. So now that we have done this a bit of pre-processing, we start building our extensive form game. So we start by drawing a root node and assigning to it the initial facts. And now we are going to be querying the choice rules to see what actions are available from this root node. Again, we have this very simple case where anyone with the role of prisoner can either cooperate or defect. And since we have two prisoners, the consequences of this is that now both Alice and Bob can either cooperate or defect. So given these results, we now build the subtree skeleton that emanates from this root node based on the actions that are returned by the choice rules. And now what we need to do is to loop over these new terminal nodes and using the control rules, see what new facts hold true at these terminal nodes. So for example, we're going to see what happens when we examine terminal node 4. To get here, both Alice and Bob cooperate, and when we query the control rules to see what are the effects of taking those actions, we find that the round counter goes to 1 as opposed to the initial of 0, and now the payoff of Alice and Bob is increased by 6 units, so starting from 0, it is now 6. And these facts are now assigned to these terminal nodes. Okay, and so once we have done this with all of our terminal nodes, we just iterate this process. So again, now we would, the game engine would move to node 4 and find which actions emanate from it and which are the effects of those actions. So if we iterate this process, setting that the terminal conditions are triggered after 3 rounds of the game, we can automatically build game trees such as this. But and just one last thing, that once we have these game trees, this can be analyzed using the game theoretical solution concepts. So in our implementation, we are providing the necessary functions to compute the Nash equilibrium coupled with backward induction, which is the same as saying subgame perfect equilibrium. This finds the equilibrium strategies given the structure of the game, which then induce a distribution over outcomes, which can then be evaluated with whichever evaluation function you would like to implement. Okay, but so one of the most important features of our contribution is that if we find that the outcomes are not satisfactory according to whichever evaluation metric we have set, we can introduce new rules with priority over higher than 0. So in this case, these are the rules to limit the consecutive number of defections in a regimented manner in the iterated prisoner's dilemma. And if we again automatically query the action situation description, including these new rules, we can find that now the game tree structure has slightly changed. So now there are some nodes at which players only have one action available. And yeah, this you can implement whichever new rules you would like to examine. So here I'm showing you sort of the template to use our model. This is so once you have written your action situation description using this action situation language, which is implemented in Prolog, you can move over to Python to automatically interpret and display the generated game tree and also find the equilibrium strategies and the distribution over outcomes that those induce and evaluate those using your custom evaluation function. So I will now very briefly go over a couple of examples that we have modeled using this framework. So the first is Axelrod metronome scheme. This is sort of analogous to the prisoner's dilemma in that you have a player I that can take a defect action to gain a benefit for itself at the expense of others. But if it chooses to defect, then there's a 60% chance that it will be detected by a monitor J. And then this monitor J can choose to either sanction or not sanction I, and this sanction it carries some cost also. So with the current utility structure that this game has, there is an incentive for agent I to defect and agent J to turn a blind eye on the defection. So one proposal that is explored is to introduce a monitor for the monitor. This is called a meta monitor. Sorry. So if player J has turned a blind eye to I's defection, then there's a 60% chance that the meta monitor K will detect J negligence, and then it can again choose to sanction or not sanction J. But unfortunately, with this payoff structure, there's not an incentive for anyone to do its job. So I still incentive to defect. J is incentivized to turn a blind eye, and K is also incentivized to turn a blind eye on J's neglect. So this is not very encouraging. But the next example is a bit more encouraging. So this is taken from Ostrom's fishing game, which models an open fishery where there are fishers competing for spots. And it is modeled that in the default configuration, players fight for spots and violent outcomes are predicted for about 50% of the time. But they can introduce some new rules to introducing allocation schemes. So for example, if a first in time, first in right rule configuration is introduced, the fisher who gets to the first spot gets to keep it. And these with violent outcomes are avoided. And also they can introduce the first to announce first in right rules, where a fisher is denoted as the announcer, and if it announces a spot that then it gets to keep it. And we can automatically analyze that implementing these rules leads to the avoidance of violent outcomes and also to honest announcements. So the announcements, so the announcer fisher actually goes to the spot they said they would go to. Okay, so just to recap, I've presented our work on the formal description of action situations and their automatic interpretation and evaluation. There are several future directions into which this could go. So the first would be to introduce dynamic boundary and position rules. So the participation of agents can become an action itself, that they can choose to participate or that they can choose to take a role. Also, a bit more challenging would be the introduction of information rule types, because information is quite a complex topic in game theory. And the last one that I find the most interesting is to explore links between different action situation descriptions and also levels of nesting. So how outcomes in one action situation affect variables in another action situation. And for this, we have a lot of literature in computer science on multi-context systems that we can draw on. So that is all, and I'll be happy to take any questions from the audience.
All right. Wonderful. Thank you for that. I'll just turn that off. All right. We'll open up the floor now for any questions that anybody has. Anyone? Let's see. Evan, go ahead. I saw your hand.
Okay. Yeah, I'm still trying to get my head around this because it's so fascinating and new to some of us. But you had mentioned the analysis of the extended form games. And I was wondering if you might be able to expand on that. And you said you did that in Python. How you go about doing that?
Okay, so fast forward, we have action situation description. This is interpreted, and this interpretation results in an extensive form game model of the interaction, right? So once you have this model, you can use, let's say, definitions from the game theory literature to predict which actions the players will take within this game. Okay, so this is the format that this takes. It's, let's say, an assignment of, you have a node from which a player can take several actions. So a strategy indicates, okay, once you're in that node, you should perform action A X% of the time, action B 100 minus X% of the time. Okay, so once you have this information for all the nodes over the game, this induces you take the path from the root node to every terminal node, you multiply the probabilities that are given to those edges by the strategies, and the terminal nodes have an induced probability to those. Okay, and then you need to build a custom function to evaluate how good your outcomes are. So for example, in the Fishers game, we decided that a good outcome was if Fishers didn't fight over a spot. So let's say if Fishers in this outcome fight, let's say assign a +1 to it or assign a -1 if they do fight. Okay, so and then you just need to weight that function by the probability distribution that you have obtained. And all of this process happens, let's say, happens in Python, okay? Because the extensive form game is constructed as a Python object, and any computation that you run on it is based using Python. So I'm hoping that clarifies matters a bit.
Anyone else with any questions? Nick, go ahead.
Yeah. Hi. Great. It's so great work. It's amazing to see what you've done so far, and it's super interesting for me. I just was curious, kind of like, what are some of your next steps thinking about, like, taking this out, trying to apply it to maybe case studies or other examples of that? Do you have any ideas of what might be a suitable or kind of more tractable areas to where this might be, a great tool for? I mean, I'm sure it's probably applicable in multiple places and multiple domains, but are any of that stand out to you as possibly where you might head with this next? Just have thinking about, how can we, what data sources might you need for this? Like what are some of the parameterization that you might go through for kind of taking this out and putting it? I'm just curious, but thank you.
Yeah. Yeah, thank you for those questions. So one area that we are, let's say for the moment, hypothesizing about, given also the background of research that we have in the Institute, is on automated negotiation over norms. So in automated negotiations, you have agents negotiating over outcomes, and those outcomes can be anything, right? But there's very little work on having those outcomes be a set of norms that the agents agree upon. And this would also come to the nesting of different action situations. So Ostrom had a classification of action situations according to operational level and then collective choice level and then a few other levels. So far we have hypothesized, well, we have used this framework to model operational choice levels, but how can we use this to go to the collective choice levels and see how all the variables lead to the final outcomes? So I'm afraid you're muted.
Yeah, I think you're muted.
Great. Thank you for your response. It's so interesting about how my brain's trying to sort of wrap around all of this kind of right now, but it's so cool to think about where you're in my head with this. I think it's also thinking about kind of like the use of information rules in modeling as well, thinking about how information rules, I mean, I know they're harder to model and kind of harder to probably pick up in some cases, but thinking about how those might also come into play with this a little bit more and how they have to take interactions and also just super cool. So yeah, great work. I'm excited to see where you go with it. I can't wait.
Yeah, thank you. So information rules are hard because let's say there's a lot of game theory solutions that work if you have sort of a very restricted type of information, which is what's called so imperfect information on sets of nodes that don't cross over multiple layers. Something similar to that. So if you want to go to more context scenarios, it's very likely that many of the solution concepts that you can rely upon no longer apply, and you may need to go to other techniques. that is something that we're exploring. So for example, if you don't want to build the full game tree because your model is too large, there are too many variables, too many agents involved, there's also something called Monte Carlo tree search that that you can use to compute approximations to the equilibrium. So yeah, there's definitely a lot of directions that this can take.
Any other questions for anyone?
Hi, can I ask a question?
Yeah, go ahead.
Since your presentation, I'm a PhD student at the medical school. Thanks for yes. Because I have looked at this paper and it was published as artificial intelligence. So I want to ask that is it difficult, easy to explain to the reviewers that in other discipline and not in the PL political science discipline that IED is important, and what the challenges you have faced when you tried to publish such a interdisciplinary research? Yeah, thank you.
Yeah. Okay. So for some context, so I'm doing my PhD, so I haven't been in research for a ton of years. This is just a couple. So the reviewing process in artificial intelligence was surprisingly smooth. The reviewers didn't have a ton of objections on the content of the papers. They did have many objections on matters of presentation, but so this might be the case because the reviewers were working on a field that is adjacent to this and already kind of understood the importance of the work without needed to make a very big case for it. But yeah, that is the experience that I had with this paper. I'm not sure it's you can generalize based from that, but that was my experience.
Any other questions from anyone else? Right then on that note, we will wrap up this month's seminar. Thank you once again to Nieves for
Thank you.
For agreeing to come on and for presenting your work to everyone. And we look forward to seeing everyone else at the March seminar, which I think is also the 7th. Yep. And yes, do check out to kind of reiterate what I was talking about at the top, do go check out those IGRI events that we are currently have the calls for registrations and applications. See if you're interested, send in by the deadline, share it with people who might be interested. And yeah, we look forward to seeing everyone next month. So have a good rest of your day wherever you are.
Thank you, everyone. Bye-bye.